also give concluding remarks. So that should be exciting. And yes, now the floor is yours, 80 minutes. Thank you.
Great, thanks, Simon. And thanks again to the organizers for inviting me to be part of this summer school. It's been a lot of fun. I've learned a heap from it. And I think that many people here have as well. This talk is going to be, as we said, it's on the theory side, but hopefully the kind of theory that's useful for applications, and hopefully the kind of applications that you'll be working on over the coming years. So I'm drawing from chapters 8 and 9 of a book that I mentioned in my first lecture on the opening morning. That's joined with Tom Sargent. I'm just wrapping it up now. The chapters 8 and 9 are where we get into kind of like dealing with the most general set of models that we handle in the book. And then we have a paper as well, which is called Completely Abstract Dynamic Programming. So a lot of this...
Sorry, these slides are in GitHub.
They are, yeah. Yeah, I noticed there's a 19 Stachurski, so I have kids pass.
Which is not.
Sorry?
That's okay. So for everybody who wants to look at the slides, they are in the repository. It's just in the first, in the earlier folder.
Okay. Thanks, Fedor. Yeah, so this was inspired by a book by Dimitri Bertsikas, this line of thought. So he has a little book called Abstract Dynamic Programming, which I took it with me on a trip. And the only reason I took it on this particular trip is because the book was small. I was looking for something light that I could stick in my bag and read on the plane. And then I started reading it, and it's just like, yeah, light bulb. This is a great way to think about dynamic programming. And it allows us to handle a really wide class of models. So chapters 8 and 9 are kind of like our interpretation of this book. And we've added things into it and just melded it a little bit in ways that we think will be useful for economists. So that's essentially what it is. Okay, so what we're looking to do is we'd like to be able to handle a large range of dynamic programs from within one set of theories. And the kind of things that we'd like to handle are the things that we see people using in applications. So state-dependent discounting is something that we mentioned on the first day. And then we have things like recursive preferences, quantile preferences, adversarial agents, ambiguity, continuous time, etc., etc. These are the kind of things that we see people using more and more in dynamic programming. And we'd like to be able to handle all of this stuff if we can. So that's the agenda. The other thing is that if we look at all this stuff and we take dynamic programming theory and we try and extend it and generalize it so that it can handle all of these things, then we naturally need to strip away structure and start with something that's much more abstract. And when we move to something that's more abstract, A, we can clarify the proofs a bit more and see what's really important for them. But B, we can look at different dynamic programs and see if there's relationships between them. So if I've got this type of dynamic programming problem, and I've got some other one, and they look pretty different. Sometimes if we strip away the structure, we can see that there's common features there. And if I learn from this one, it can tell me something about that one. And the more we abstract, the clearer these connections become. So that's the value of moving to this more abstract kind of representation of dynamic programming. What I'm not going to talk about here is things like approximation methods. I'm going to set that all aside. And in fact, everything I'll talk about in detail today is finite state and action spaces. So I'm not going to discuss the extra layer that comes in when we start approximating value functions and approximating policy functions. I'm just going to put that aside. And I'm putting it aside mainly because we've already got plenty on our plates for an 80-minute talk. So I just want to set that aside But of course it is important, right? How does this stuff interact with the algorithms that we're going to discuss? So we've talked a lot about what kind of approximation architectures are good at approximating a large class of functions well. We talked a lot about that, but the other issue that comes in when we think about dynamic programming approximation is how well do they interact with the algorithms. That's kind of a separate topic. So there are some answers to these questions. There's a book called Neurodynamic Programming, which was published in 1996. So way back in 96, they're already looking at topics like this, integrating neural networks and dynamic programming. And these authors are very smart cookies, and they've done a lot of really high quality theoretical work. So I can't tell you a lot of the details of what's in the books and the subsequent literature. I've worked in the area a little bit, but that's something that I plan to do a lot more of next year. And I have promised, or Tom and I have promised to write a second volume of these books on dynamic programming. And that's hopefully going to come out around about the end of next year. And in that book, we'll handle things like continuous state and action spaces and integration of these approximation methods with the algorithms. But for today, let's leave this stuff out. All right, so what I'm going to do is I'm going to start with a really standard model, and we'll discuss it in some depth. In a way, it's not super necessary to cover all of this stuff, but I want to go over the notation in concrete setting. And once we've done that, we can shift to the abstract setting, and we'll see what we're abstracting from. It'll give us a basis for thinking about those abstractions. This standard model is going to be a Markov decision process, which is perhaps the most standard environment for thinking about dynamic programming. As I said, everything's going to be finite, so the state space is finite and the action space is finite. We're going to look at how we solve this model, what the algorithms are, and then we'll shift up to more general problems. Now, I should say that this particular problem is easier than the problem that I discussed in the first lecture on the first day. It's a special case of that. So I think we can go through it reasonably quickly, but if there's anything that's not clear, please stop me, and I'm happy to chat. Okay, so Markov decision process, we've got a finite set X, we'll call the state space, finite set A, the action space. We've got a feasible correspondence gamma, which is a correspondence from the state space to the action space. And gamma of X is going to have the interpretation as before, as the set of actions that are available in state X. Given a current action A and a current state X, the next period state X prime is going to be drawn from this probability distribution. We also get a current reward, R of XA. We have a constant discount factor. So unlike the previous case where that was moving around with the state, we're going to hold this guy constant. And then lifetime reward is going to be evaluated something like this. When I first studied dynamic programming, I found it really confusing because I just didn't understand what this expectation meant. Because, like, what are these guys, these actions? If we're maximizing something like this, I don't really know how to take this expectation until I can kind of like pin this guy down through the dynamics, preferably of X. So the way we get to understanding these lifetime rewards is by thinking about policy functions, which I'll get to in just a second. But before we do that, to clarify, the Bauman equation associated with this dynamic programming problem is this equation at the bottom. Okay, so I think pretty straightforward so far. A few more definitions. So a feasible policy is going to be a map from the state space to the action space that respects the feasibility constraint. I'm assuming, by the way, that this guy is not empty for every X. There's a map from states to actions. And cap sigma is going to be the set of all feasible policies. And then this notation, you'll remember from the first lecture, the notion of a V greedy policy. So what we're doing here is I just take the guess of the value function, if you like, this function V or an arbitrary function V on the state space. Treat it like the value function. I put it in the right-hand side of the Bellman equation, and I maximize it with respect to the feasible actions. So a policy where sigma of x is in this argmax for every x, we'll call that a V greedy policy. Treat V as the value function and maximize. The Bellman operator has the obvious form given the value function, given the Bellman equation. And the policy operator, so the policy operator is similar to the one that we saw when we were looking at state-dependent discounting. In fact, it's the same when the discount factor is going to be constant. So one of these guys is maximizing at every x. The other one is fixing a policy, feasible policy, and just taking that as the given action and shifting to the next period. So you'll see that if sigma is V greedy, the statement that sigma is V greedy is equivalent to this statement. And this statement here, so if you start thinking about abstracting, if I think about abstracting, I kind of like this definition, because this is a very abstract definition. This definition has a heap of structure in it. This definition has very little structure. This is another way to think about V greedy policies, which we can use as we shift into a more abstract set. All right, so here's a picture that we might get if we had a single state. So it's just one-dimensional. Obviously, no interesting dynamic program looks like this, but nonetheless, it's potentially helpful to visualize the idea. We've got a set of policy operators, and then the Bellman operator is going to be the upper envelope of the policy operators. Yeah.
When in the preceding slide, you had TV. Is that a product or is that a name of a single function?
So V is a function and T is an operator. So T of V is a new function.
Yeah.
And this equality here is
just like a function. Could I say like T of V?
T of, exactly, yeah. I'm just writing without the brackets, I guess, because it's an operator. So that's all it is. Thanks for clarifying. Yeah.
Maybe I don't get it either, but T is a mapping from what space to what space?
It's a map from the set of candidate value functions into itself. So yeah, so this kind of picture is like confusing in a way because the situation is high dimensional. And I'm saying, all right, let's imagine that it's one dimensional. If it's one dimensional, then it might look something like this. If it's one dimensional and we have very few policies, it might look something like this. Yes, I'm just reinforcing the idea that the Bellman operator is going to be the upper envelope of the policy operators. Okay. So back to concrete. This is just definitions and notation. So R sub sigma, I fixed the policy sigma, and R sub sigma at x is just the rewards that I get when I fix this policy. Sigma of x is going to be my action at x, and therefore my rewards are going to depend purely on the state. And likewise, the transitions are going to depend purely on the state. And of course, this guy here is now just a Markov matrix. So when I pick a policy, I close the loop in the dynamics. So picking a policy is akin to picking Markov process, the dynamics of Markov process, plus a reward function. And then the lifetime value of the policy sigma is going to be given by this expression. And here the x's are generated by p sub sigma. We can simplify this expression a little bit. If I take v sub sigma of x, all I've done here is I've taken the expectation and passed it through the infinite sum. And I get something like this. And what's this guy here? It's just the expectation of this function r sub sigma with respect to the Markov chain that was generated by p sub sigma. So this is the time t transition probabilities. So this is the probability I end up at x prime after t periods, given that I started at x. So I just sum up this to get the expectation, the conditional expectation. And this guy here, I can think of this as like a matrix operation. Since everything's finite, I've just got r sub sigma and I've got p, and I'm just summing that. So then I can write it like this, and I can apply the Neumann series lemma, which we talked about in the first lecture, which allows me to write this geometric sum in this way as well. So this is the lifetime value of following this policy sub sigma. Any questions so far? Right. So I'm going to talk a lot about the policy operators. Policy operators is not something that we tend to pay a lot of attention to, but actually for the theory that we'll do, they come to the center. They're like hard and center of the theory. We shift to a more abstract setting. On top of that, they're useful for computation. So I talked about an algorithm that directly uses these policy operators in lecture 1. Does anyone remember what that was? Sorry?
The HPI.
HPI, yeah, so you could use them in HPI. There was another one where we used them more directly. Yeah, the optimistic policy iteration. Yeah, so Howard policy iteration, we're directly computing the lifetime values. We can do that using these kind of expressions. But we can also approximate these guys with the policy operator. So if I take the policy operator and iterate with it, well, the content of this slide is that you're going to converge the lifetime value of the policy. And if I was to iterate a few times, I'd get an approximation of this lifetime value. And maybe I want to do that instead of going all the way to this lifetime value if that's expensive to compute. Yeah.
In this setup, can we think about a soft policy, a policy that introduces some probability of taking multiple actions because it will just induce a bigger Markov chain? Or do we see it only goes, it takes a...
Yeah, so we could definitely introduce randomization. In this particular setup, because everything's so regular, it's not going to achieve any higher lifetime rewards. So the optimal policy you can prove in this setting, the optimal policy is going to be the stationary deterministic policy. I've kind of omitted that story entirely, but that's an important point. Okay, so this is the policy operator. The unique fixed point of the policy operator is the lifetime value of that particular policy. And we can easily prove in this case that this operator is globally stable. So when we iterate with it, we're going to converge to V sub sigma, the lifetime value, the unique fixed point. And you can prove that, for example, with Banach's fixed point theorem. So when we shift to more general cases, that's something that's going to potentially go away. But at the moment, we have it. Okay, so then to state an optimality theorem, we have to define optimality. We define the value function as the pointwise max of the lifetime values over the set of feasible policies. So at each x, maximize over the set of all possible feasible policies. That value is equal to V star value function. Or equivalently, I can write V star like this as the upper envelope of these guys, as the supremum of these guys, the pointwise maximum of these guys. And a policy sigma is called optimal if it attains V star, if it attains the maximum lifetime value at every x. So these functions are equal. So we have equality at every x. Okay, so then really standard optimality result says that for a Markov decision process with Bellman operator T and value function V star, V star is the unique fixed point of the Bellman operator to use a contraction mapping. A feasible policy is optimal if and only if it's V star greedy. Then at least one optimal policy exists. So these are all our standard optimality results. Most standard optimality results. And this one might sound a little bit unfamiliar, but all I'm saying is that a policy is going to be optimal if and only if you take the value function, you put in the right-hand side of the Bellman equation and maximize with respect to that over the actions. That will tell you the optimal thing to do.
And sorry, why do you say at least one? I mean,
at least one optimal policy exists.
Yeah, like within one, if it's like a transaction.
Or, so there can be many optimal policies. So for example, if you look at the definition of a greedy policy, the maximizer is not necessarily unique. So we would need more structure to get uniqueness.
So B may be unique, but sigma may not be.
Correct. Okay, so then we have standard algorithms. These are essentially identical to what we talked about on the first day. The only difference out of all of them is the computation of lifetime value. It's slightly different that appears in Howard policy iteration. So value function iteration looks exactly like we saw on the first day, standard algorithm. So we won't dwell on that one. Howard policy iteration. So in this case, I take a policy, I compute the lifetime value of that policy. And I probably should have written this in here, but computing the lifetime value of this policy, the natural way to do that would be to use this expression here. That allows us, at least when the state space is moderate to small, that allows us to get the lifetime value of the policy.
Can I ask you probably a stupid question here? And I know you said you work with finite finite amount of samples in state space. So one of the things in practice when you go to continuous states is if you take one of those policy iterators, iteration, policy iteration, you converge typically quicker to an equilibrium rather than when you use value function iteration. But there's very little theory around that.
Yeah, so
that's what you show here. Do you have a notion how this translates to continuum of states? Or?
It really varies problem to problem. Yeah, so if you think of time iteration, or what economists call time iteration, that's essentially isomorphic to value function iteration. You're just doing, there's a one-to-one mapping between value function iteration and time iteration. So in theory, they move at exactly the same rate. In practice, we rarely find that they do. Now, typically, you're going to find that time iteration converges faster. And the main reason is that you're using more structure from the problem. Particularly, you're using the fact that this problem has an Euler equation. So in general, we're not going to have, for an arbitrary Markov decision problem, we're not going to have an Euler equation. In this case, we do. Now, if you use that structure and exploit it, you can get things running faster. And then if you use even more structure in that, like the endogenous grid method, for example, it's running faster again. In theory, running at the same speed, in the sense that the iterates are moving together, but in practice, we can compute these iterates faster and more accurately by exploiting additional structure. Yeah.
Sorry. Can I think of policy function iteration as applying one-shot deviation principle to dynamic programming?
I wouldn't know. I'm not sure. Yeah, I don't know enough about it to say. I haven't heard anyone make the connection. That doesn't mean it's not true. Yeah, so this Howard policy iteration, I guess this is the one that you're talking about. So we discussed it when we talked about solving a problem with state-dependent discounting, and the story here is exactly the same. So it's basically Newton iteration on the Bellman operator, on this operator T. So we can easily do, if we have the Bellman operator T, which is going to be this blue line here. So underneath this, you can imagine that there's lots of these orange lines. These are like the support functions. So the Bellman operator is going to be the upper envelope of these guys. And you might also remember that we said that if I take some V and then look for the policy that's V greedy, it's exactly the policy where T sigma and T agree with each other. So we had that kind of like abstract definition of a V greedy function. So that means that we've got equality here. And then from here, if I'm going to use Howard policy iteration, I jump to the lifetime value of this guy. And then I take the greedy policy and then lifetime value, and that's exactly Newton iteration. Whereas value function iteration is simply just iterating on this blue line, fixed point iteration. So boom, boom, boom. Something like that. And then the third algorithm we discussed in the presentation here is exactly the same. Just the definition of the policy operator changes slightly as optimistic policy iteration. So we know that, so with Howard policy iteration, we take policy, we get the lifetime value of the policy. It's function V. And then I take a greedy policy from that guy, and then I get the lifetime value, greedy policy, lifetime value, and we go round and round. Optimistic policy iteration is similar, but instead of taking the lifetime value, we're just going to approximate it. We're going to approximate it by iterating with the policy operator. So in the picture that we had before, we're going to take this policy operator and I'm going to do some iterations with this guy, which is going to get me close to the fixed point. But before I actually get there, I'm going to jump to the next greedy policy. So under the stated conditions, all of these algorithms converge. Value function iteration, Howard policy iteration, optimistic policy iteration, they're all going to converge. And because the state and action spaces are finite, Howard policy iteration is going to converge in a finite number of steps. So for details and proofs, you can see chapter 5 of the dynamic programming book that I've written with Tom, but these results are old. They go back to the 1960s, 1970s. There's lots of places you can find the proofs. Okay, so now that we've just recalled some facts about the basic model, let's shift to something a little bit more interesting. Let's look at some extensions to the basic model. Actually, what I said is not just extensions, but modifications and extensions. So we look at extensions, we look at modifications, and we'll look at modifications of extensions and so on. So mixing all these things together. So one modification of the basic model is we might decide that it's more attractive to work with the expected value function rather than the value function. And this is something that John Russ pioneered back in 1987, working with expected value functions. And around about the same time, Q-learning came on the scene. And these guys are doing something, at least in the basic dynamic programming formulation, rather similar, in that they're manipulating the Bellman equation. And instead of working with the value function directly, they're working with what they call Q factors. So in some situations, it might be preferable to work with the expected value function rather than the value function. So let's define gxa to be value function after I've taken the expectation. So this is just an arbitrary function b at this stage. But if we look at this expression here and we insert it back into the Bellman equation, and we start manipulating, and we manipulate the Bellman equation that we saw before to eliminate v from it, and write everything in terms of g, you get an expression that looks something like this. So without r, this is a variation on the Bellman equation, and if I put r in, then it's a variation on the Bellman equation. And I guess the nice thing about it is that we get to switch the order of maximization and expectation. And that turns out to be valuable in a range of different applications. Yeah.
Could you give some more intuition on what the expected value function means? Imagine the value function is 100 and the expected would be 101. Wow. What's the difference?
I don't give intuition on these things. I'm a maths guy. I'm not interested in intuition. Yeah, look, I don't know. I mean, I think there's a lot of other people here who could answer that question better than I can. My understanding is simply that this is a mathematical convenience that allows us to rewrite the Bellman equation and the Bellman operator in a way that reverses the expectation and the maximization. Maybe Fedor would say things differently, or John Russ, but I think this is basically reversing the order of these things to get the expectation on the outside. Turns out to be convenient.
Also shrinks the state space.
Potentially shrinks the state space, depending on the application.
Depending on the application, it can reduce the dimensionality of that explained.
Yeah, yeah. So I guess there's those two benefits. I mean, in some situations, it can increase the size of the state space in a sense, because now I've got a state and an action. Yeah, so it does depend on the application. Intuition, it's not my strong point. Sorry, that question was first. Yeah, go ahead.
Is there an expectation inside of that B that's inside of the other expectation? Like you have g of x of a equals an expectation over v of x prime in the top one.
This guy here?
Yeah. Is there an expectation also within B?
Bound up in here?
Yeah.
No, not necessarily. So for this simple MDP, I would say no. I mean, I'm just taking this G as the definition. I plug it into the Bellman equation, and I mess around until I eliminate all the V's and just have G's. So now I've got a Bellman equation in terms of G. Once I solve that guy, I can potentially go backwards and forwards between these two things.
Okay, so there's no like expectation inside of an expectation.
There's no. I guess there could be, depending on the application. There might be another expectation that's lurking inside here. There's all kinds of variations on this idea. So potentially there might be.
Yeah, so it actually goes to the same question. So the value function would usually have an expectation, right?
The definition of the value or the Bellman equation, you mean?
The definition of the value function, right? Because she is saying what is the expected lifetime value, right?
Mm-hmm.
And then when you put an expectation on the outside, is it then the law of iterated expectation that is used to move the inner expectation?
Oh, I don't think so. I think at I think you have to separate in your mind the value function, which you just described really well, and solutions to the Bauman equation. And these are potentially different things. This is just a functional equation, right? Now, it may happen that these two things coincide. If that's true, great. If not, maybe you have problems. I think that's a better way to think about it. Any more questions, comments? Okay, so this is a modification. Now, instead of modifying it, let's change things a little bit. So let's take our Markov decision process and insert something like Epstein-Zinn preferences. Epstein-Zinn preferences, we're doing two things. One of them, forget about the alphas for the moment. Pretend that alpha is equal to 1. And just think about this gamma guy here. So what we're doing there is we're kind of twisting this conditional expectation. I put the gamma on the inside, and I take the sum, and then I've got 1 over gamma on the outside. So I transform, take the expectation, and reverse the transform. So this gamma is intended to parameterize attitudes toward risk. Since they're bound up in the expectation. And this alpha guy here, you can see, if you forget about the gammas, just think about these two terms, this term to the alpha, this term to the alpha, all to the 1 over alpha. So that's just CES aggregation. Instead of adding things, we're just going to combine them using CES. Okay, so is this a good idea? Well, it depends on the application. So having talked to Christian and Frank, these guys are doing some pretty hardcore climate modeling, and they're building Epstein-Zinn preferences into their model. You see a lot of this in asset pricing. And you see more of it creeping into macroeconomics as well. And then potentially there's other fields I don't know about where Epstein-Zinn is being used. Okay, so with Epstein-Zinn, we've introduced a fair bit of nonlinearity. And the question is T still a contraction? So a lot of the theory of the basic model is built around the fact that T is a contraction mapping. Does anyone know the answer to this? The answer is no. In general, no. Maybe in some special cases. In fact, when I started working on this, I was working with a guy who's in macro finance, and I worked on it for a couple of weeks, and then I went to him. I was really happy, and I said, yeah, I've proved that this guy's a contraction mapping, at least for this set of parameters. And he said, no one cares about those parameters. They're completely irrelevant for applications. I was like, damn it. So I had to go back and look for other fixed point theorems. So things start to break down when we introduce these nonlinearities, and then we have to ask, are these optimality results still valid? And then do the algorithms converge? So that's one complication we could introduce. Another one that we could introduce is so-called risk-sensitive preferences. Has anyone worked with this at all? Okay. Was there a reason you might prefer that over Epstein-Zinn? I mean, they're kind of similar in a way.
They are all super closely related, right? I mean, there are reformulations, and also I think the Epstein-Zinn you can sort of reformulate risk sensitive, and then they might have different conversion protocols.
Right, but in general, I mean, we don't have the CES kind of aggregation structure here that we do.
But you can transform them into each other, basically.
1 for 1?
I think pretty much. Depends on the problem, I guess.
Okay, we have to talk more about this.
So yeah, this guy you can, yeah.
Because this is a contraction mapping.
Yeah, and I use the Epstein-Zinn actually in that reformulated way in order to hopefully contract better. But I can
Okay, that's super interesting. Okay, so we'll chat more about it. Okay, so this kind of risk-sensitive preferences, it's something that people like Tom Sargent worked with a lot. And it seems to be popular also in the modern computer science reinforcement learning literature. Theta is a parameter that's used to parameterize our attitude to risk. Theta below 0 means we're risk averse, with it like this. Theta above 0 means we're risk. Yeah.
So certainly these risk sensitive preferences, they look a lot like this kind of log sum. You have these history based shock kind of max expression. Is there like a connection between?
I don't know. Yeah, it's a good question, but they do, don't they? Because you've got the expectation inside the sum and then the log on the outside.
That would be just a dynamic discrete choice problem. That's the expected value function. If you add extreme value shocks, that's exactly the Bellman equation you get in the discrete choice model.
And where does theta come in?
What?
Where does theta come in there?
The states are we integrated out an unobserved state called epsilon. And so then it's just expressed in terms of states and actions.
I see. And would theta have an interpretation there that's connected to risk?
No, well, no, it's in this case, it's just
a scale parameter.
Idiosyncratic shocks.
It's the scale of the transition probability. There's a transition probability under the law.
Oh, it's in the law. Yeah, ours is on the outside. Right.
Some similarities and some differences. Okay, so that's another complication that we might introduce. And then we might say, hey, let's mix and match. So let's have risk-sensitive preferences, and then let's throw in state-dependent discounting as well. Or maybe we take Epstein's in and we put in state-dependent discounting, and then we have to ask the same questions. Is the Bellman operator still a contraction? Are these fundamental optimality results going to be valid, and do the basic algorithms? You can see here the state-dependent discounting, so beta is a function. And then as we start to look more into the literature, we see that there's more and more complications that we can potentially introduce here. So we could start throwing in something like ambiguity, maybe with a smooth ambiguity model. Or maybe we could take Epstein's in, but instead of working directly with the Epstein's in Bellman operator that I showed you, we might want to transform that into expected values, like we did with the original Markov decision process. Maybe there's some advantage to doing that. In fact, there potentially can be advantages to doing that in terms of what Fedor meant, which is reduction of the dimensionality of the state space. Or maybe we want to work with ambiguity, expected values, and state-dependent discounting. Or maybe instead of expected value functions, we want to work with something called integrated value functions, which also appears in the dynamic structural estimation literature. And we want to do that in a risk-sensitive framework, and we want to do it in continuous time. So you can see that we can take all these different complications, and then we can start mixing them all together, and we get this potentially very large set of problems. So then the question is, like, is there any unifying theory? Or are these problems just like simply too diverse? We can't really say anything useful. They're just too different from each other. So I guess the idea of abstract dynamic programming and the things that we try to cover in chapters 8 and 9 of this book is to try to provide a useful general theory for all these different kinds of models. And, you know, do we solve every single one of these problems? No, definitely we don't. But we, at least I think, give a starting point, right? Like halfway down the path. And the rest is left to you guys. Hopefully complete the journey. Okay, so there's two levels of abstraction in the book. One is what we call recursive decision processes. And then there's another chapter after that, chapter 9, where we really go crazy with the abstract stuff. This is actually potentially useful, believe it or not. And I might get to that if we have time, but let's go slowly rather than fast and see how far we get. Okay, so with recursive decision processes, we start off, the idea is pretty straightforward, really. What we do is we're just going to take an abstraction of the Bellman equation. So we abstract the Bellman equation, and then we're going to state optimality results in this framework, and then we're going to see how nicely we can fit the different applications into the framework. The ideas for abstract dynamic programming goes back to a beautiful paper by Eric Donato that was published in 1967. So they're old ideas. He's treating the case where everything's a contraction. And then, as I mentioned before, Dmitry Bertzikas has a very nice book on the topic, which is going further. My co-author Takashi Kamihigashi has some nice results. So we take these ideas and we build on top of them to create something that we hope is useful for economists, for you guys. So the first step is to begin with a generic version of the Bellman equation. Everything, all of the structure of the problem is wrapped up in this abstract description of the right-hand side of the Bellman equation. In the setting that we'll consider here, I'm going to take the state to take values in a finite set, fx, and the action is also going to be in a finite set. Later we get into discussing more general state spaces, but let's just leave it in this finite setting for now, where the results are cleanest and clearest. But like one of the reasons I like this theory is that so essentially what we're going to do now is we're going to take this abstract description and we're going to see what kind of properties it needs for us to have a nice from optimality theory. And we'll see that, with fairly simple structure, we can get a pretty nice sort of optimality theory based on some simple properties that we place on B. Yeah, let me keep going. Okay, so let me say it like this. Okay, so let's formalize this idea. So we'll say a recursive decision process is going to be a triple. We've got gamma, which is going to be a feasible correspondence. We've got V, which is a set of candidate value functions. And we've got this object B, which is the right-hand side of the Bellman equation. And this guy is going to wrap up, I guess, all of these potential issues like recursive preferences and so on. And you can also see we don't really have any specification of dynamics there either. So all of this is just folded into B. So I suppose the nice thing here is that we can set down an optimality theory even when we get to fairly complex models without having to talk about a whole lot of measure theory and a whole lot of functional analysis. So for example, if you try and learn dynamic programming by reading the book by Stokey and Lucas, is that the way most people learn dynamic programming? You didn't really read the book. You didn't really read the book? Okay, so I personally found this a painful experience. I think the issue is that it doesn't really separate out the dynamic programming theory and what's actually important there from all of the measure theory and functional analysis that we need if we're going to deal with specific problems in certain situations. So let's just put all that aside. Let's get the theory of dynamic programming, and then we'll look at our particular application. And if we really need to deal with all this stuff, we'll deal with it. But if we don't, we won't. Okay, so so formally, we've got three things. We've got feasible correspondence, just a non-empty correspondence from states to actions. This notation you've all seen before. So this cap sigma is going to be the set of all feasible policies which are maps from states into actions that respect the feasibility constraint. V is a subset of the set of possible value functions. value function is just a map of the state space into numbers. This is a set of candidate value functions. And then this object B, which we'll call the value aggregator, just to give it some kind of name. And this takes a feasible state action pair and some guess of the value function and gives us a number. And of course, we need at least a little bit of structure to make sure things are gonna go relatively smoothly and we can define optimality and so on. So the structure we'll assume is that there's some degree of monotonicity here. So if our candidate value function goes up, then lifetime rewards based on that valuation, future states is going to go up. And this is always true in applications. I've never come across an application. I'll show you examples in a second, but this is like a trivial thing. It's always going to hold. And then this consistency condition, we don't even need to talk about it, but it's just like, did you choose this class of value functions carefully so that it's going to catch the objects that we want? So these couple of conditions will be trivial to check in applications. Are they the only conditions we need for an optimality theory? Sadly, no. There's still more yet to come, but if we have this stuff, then we can define the things that we want to define at least. But before we do that, let's just think a little bit more about the definition of a recursive decision process. So every Markov decision process is a recursive decision process. So I've already got, if you give me one of these guys, and this is the model that we studied at the start, Markov decision process. If you give me one of these guys, or I've already got a feasible correspondence, I take V, my set of candidate value functions, as let's say every possible value function. And then this B guy is just the right-hand side of the Bellman equation. And if I define B like this, so these are my three objects, and if I define B like this and we put it inside our abstract Bellman equation that we started off with, we recover the Bellman equation from Markov decision process. Yeah.
It seems like this framework doesn't include, system of value function equations like search and matching model. So can you extend the framework to include these multiple value functions? Seems like
it's a really good question. So it does include them, and the way it includes them is that if you think about these multiple value functions, let's say I've got two of them, for example. I could think about them, maybe it's job search and I could be employed or unemployed. I got two different value functions. What I could think of is that there's an extra state variable. So instead of just V of W, where W is the wage, and I've got another state that says I'm employed or unemployed. And I switch this guy around, jumping between these guys. So just by treating that as a state variable, we can plug it into this system. It's not as intuitive in a way, but we can definitely plug it in. Yeah. Any more questions?
Right. Both on tonicity. So E is a function. W was a function. So this is like point definition. So
it is, yeah. So let's say I take this guy and replace it with another function that's greater everywhere. Yeah. Then is this guy going to go up? Is B going to get larger? So you can kind of see why it's always going to hold. Good question. Any more questions, comments? Yeah.
I'm sorry, this is really basic, but so V is a subset of Rx, but it's a map, right? It's a candidate for the value function?
Yeah, V is a map because it tells us the value at any given state. So think of your state space X like this. Think of this, the value function looks something like this. It's just a function on the state space. In that sense, it's a map. State, value of state. Yeah, so when we go to like the completely abstract dynamic programming, we even throw that away. And we just say that V is just an object in a partially ordered space. But at this stage, it's a more concrete, recognizable object. Any more questions? Yeah.
Do you think strategic interactions games are included as well? So if can actions respond to different decision makers and the value functions, the value sort of depend on the other value functions in a complicated way with the best responses?
Yeah, potentially. Potentially. I mean, so for example, we might have another agent here, like maybe it's a min-max kind of scenario. And I've got a maxing and then there's a min here. Again, that's something that I can just fold into B.
Yeah, that's what I'm thinking.
Right. Yeah, so that additional structure can be just folded into B, and now we need to check that those basic consistency conditions hold. Yeah, and we're all good. That's a good question. Any more questions? This is great for me because I'm learning what people actually care about. I get excited about the maths and go off on crazy tangents. It's good to be pulled back by the audience. Yeah, okay, so good. So we go on. Okay, so optimal stopping, that would be another example. An optimal stopping problem might look something like this. So I'm choosing between exiting, and this is my exit reward, depending on the state, or I could decide to keep going, and I get some flow continuation reward. Maybe this is job search, and I could stop and just get a lifetime value of a given job, or I could get unemployment compensation, and I shift to the next period. So this guy here, we can plug that into the model. So I can just take V to be something like this. And the set of possible actions I can take to be 0, 1, would be stop or don't stop. And if I write B like this, for example, so now I'm choosing A is going to be 0 or 1. If I plug that into our abstract Bellman equation, like this guy here, if I plug that into this guy here, I'm going to recover this expression here. If I take the max where A can be 0 or 1, on the right-hand side here, I just get this. Okay, so that's again a model that we can easily plug into the framework. If I have state-dependent discounting, which is what we covered in the first lecture, the Bellman equation is something like this. To plug it into our framework, I just take the right-hand side of the Bellman equation, unmaximized, call that B, and we're good. I just need to check that monotonicity holds, right? If this thing goes up everywhere at every state, does this thing go up? Yeah, of course it does. So we're good. Right, and then we could go on and on, but you guys get the idea already. So I could say risk-sensitive preferences, something like this. So B is just going to be the unmaximized right-hand side of the Bellman equation. Monotonicity is going to hold. Sometimes, like with Epstein-Zinn, I might want to, so this is Epstein-Zinn preferences. B is just going to be the unmaximized right-hand side of the Bellman equation. What was I going to say? Yeah, so sometimes you have to be a little bit careful with the set of candidate value functions. Make sure that this is going to be well defined. I don't want to be taking powers, fractional powers of negative numbers. I don't want the square root of -1 in here. And I don't want to take a negative power of 0 and so on. So we just check that. So that's something that's appeared on the scene recently is quantile preferences. So with quantile preferences, the idea is that the Bellman equation might look something like this, where this guy is going to be the 10th quantile of the continuation value conditional on our action. So this guy here. So why would we want to use quantile preferences? I don't know. Maybe people care about the median more than the mean. And there's some experimental evidence that purports to show that we're more concerned with the median than the mean in some situations. If we care about the median, let's say, then maybe we could use these quantile preferences. Or we could have a shortest path problem. So with the shortest path problem, we're traversing some graph. I guess you guys have all seen this problem. So let's say curly G is a graph. It's got some vertices and some edges. And we're traversing these edges, trying to get to the specified vertex D, which is our destination node. Curly O of X is going to be the set of direct successors of this particular node X. The reason this is not a standard dynamic programming problem like the ones we considered first up is because there's no discounting. And actually, we could go further, and we could take beta greater than 1 here. So there are certain problems where beta greater than 1 arises. So these are again non-standard problems. Certainly there are other examples of these recursive decision problems. Just take the unmaximized, or in this case, unminimized right-hand side of the Bellman equation. That's B, check monotonicity, we're all good. So, yeah.
What about finite horizon?
Yeah, good question. So finite horizon we can embed in there as well.
The state variable.
We just take time as a state variable. So for example, it might be an optimal stopping problem. And we take t to be a state variable and it increments by 1 at each unit in time. And we just have something in the reward function that switches off once you get to some target state, capital T. Yeah, the tricky thing actually is continuous time. Continuous time is a little bit harder to embed in this framework. There is a more abstract framework, which I might talk about, where I can embed it, but maybe I'll spare you guys that. How long do I have? 15? Yeah. Okay, so then the definition of policies and policy operators and Bellman operators is going to be exactly as you expect. For example, the feasible policies are mapped from states into actions that respects the feasibility constraint at every X. And cap sigma will be the set of all feasible policies. This is what we're maximizing over. Policy operator looks like this. Seem reasonable? It's just a natural generalization of what we saw before with policy operators. For example, the Epstein-Zinn policy operator would look like this. In one particular case. Okay, then to define optimality, we use natural generalizations. So let's suppose for the moment that these policy operators all have unique fixed points. In that case, we're going to denote them by V sub sigma, and we'll interpret them as the lifetime value of following this policy sigma. So this is where we move beyond the maths to the interpretation and the intuition. But I think that this is a natural way to think about it. So we saw in particular cases, we looked at the policy operator. And we saw that the unique fixed point of this operator is precisely the lifetime value of following the policy. And then if you study things like these recursive preferences, this is exactly how you define lifetime values. Taking this guy out, to define a lifetime value, I just write down this recursive expression of what we expect it to satisfy. So it's an aggregation of my current rewards and my expected future rewards under a given policy. So the fixed points of these operators, if they exist, we'll associate them with lifetime value. And since we need to have these things, we're going to call our recursive decision process, our RDP, well posed if every single policy operator has a unique fixed point. If that's not the case, then we can pack up and go home, because the problem doesn't make sense. I don't know how to interpret that. I think at least at a fundamental level, we want to know what the lifetime value of a given policy is. If they don't exist or we have multiple ones, I don't know how to think about that. Leave that to Edward handles. Yeah.
Can we say, when we think about, I think the question also Peter posed was, when we talk about this fixed point, we're not talking about whether or not there could be multiple equilibria, thinking like that. It's rather that we will converge to the lifetime value of a given policy.
Exactly, for a given agent. Yeah. So we haven't got to the level of equilibria yet.
Yeah, so it's T sigma, right? So the L1 operator.
It's just a policy operator for an individual agent. Okay, so then, so that's the minimum we got to assume. Greedy policies we can define in the absolute obvious way. It's just the policy that maximizes the right-hand side of the Bellman equation, every x. So that's V greedy given a guess of the value function V. The Bellman operator we define in a totally obvious way. The value function we define exactly as we defined it before. And optimality we define exactly as we defined it before. So there's no need to dwell on this. Our policy iteration is quote unquote unchanged. So the algorithm is the same, but this is maybe a more interesting statement. We take a policy and then we compute the lifetime value of that policy. Well, we know how to do that for a Markov decision process, but for all these other things, the policy operators are nonlinear maps. So then how do we handle that? So maybe with Newton-Kantorovich or something. So these are interesting questions. Okay, so I'd like to say that that's all we need. This is the basic bare bones of an optimization problem. There is actually one more thing we need, and it's pretty hard to weaken this. So we've weakened it slightly, but basically we need that these policy operators not just have unique fixed points, but they're also stable. So if we take the unique fixed point and I start here and I start iterating with this guy, I converge to the unique fixed point. If I start here and iterate, so wherever I start from, I'm going to converge. If that's the case, I'm going to call this guy globally stable. So if we have global stability, then everything works. That's the core message of this whole chapter. So if you have global stability, then the value function is the unique solution to the Bauman equation. The feasible policy is optimal if and only if it's V star agree or the algorithms converge. All the basic stuff. All these fundamental optimality results are going to go through. So that's like the key message. And it's sort of good news in a way, because this is a pretty straightforward statement to say that's what we need for everything to work. But it's potentially bad news as well, because we have the task of proving that this statement is true, that all of these guys, all of the policy operators are stable. So to make life a little bit easier then, let's look for some conditions. Let's look for some conditions under which this will hold. So option one is that you can just take that theorem and go, all right, here's my crazy dynamic program that I want to solve. Now I know what I got to do. I look at these policy operators. And then option two is that you can use something off the shelf, which is in the book. So we developed a couple of things off the shelf that can be used straight away. So for example, if your dynamic program happens to satisfy this contraction property, then you're good. So this would cover all of the standard traditional models. And then it actually covers quite a few more. I guess I'm not giving much intuition for this, but you can kind of imagine, right? If this statement is true, that Banach's contraction mapping theorem is going to give you a unique fixed point. This looks like it's going to give you a contraction. Yeah.
In design, the norm.
Yeah, sorry.
I think of a norm as a sum of squares.
Yeah, that's okay. Yeah, I'm rushing because I'm getting out of time. So this infinity norm, that just means that this norm is the supremum norm or the max norm. So I take these two functions, take v of x and w of x, the absolute value, give you the difference between the absolute value, and max that over x. So it's the maximal absolute deviation between the functions. So all the traditional problems fit into this case, but not all of the problems that we've talked about. So for example, if you have state-dependent discounting, and that state-dependent discount factor is getting bigger and smaller, and sometimes it's bigger than 1, this is not going to work for you. So then there's another set of conditions, which we can skip all the details of. But this would be enough to handle models where you have kind of like a long-run discounting. But in the short term, you might be super patient, depending on the state. And then this one's kind of neat too. So this is enough to have global stability of all the policy operators. So if you think of the fixed point theorems that you know that give you global stability, there's like Banach's fixed point theorem. And can people name any more? What's another fixed point theorem that gives you a unique fixed point that you converge to under iteration of the map? Sorry. Capitani gives you existence. Yeah, that's all. Sorry? Only gives you existence. Sorry? Callisti?
Similar to Banach, but it just requires absolute.
So is it one of these variations on Banach where you contract eventually? Is that the kind of idea?
I think so. I think the main setting point is that
Okay, but it's still a basic contraction kind of idea.
Yeah.
Interesting. Okay, I'll definitely check it out. I'm an aficionado of fixed point theorems, so I'd like to know as many as possible. This one here, so there's a fixed point theorem which is due to a Chinese mathematician called Du, which I learned, and then I've since been like making a living out of applying it to 10 different problems all across economics and finance. And it basically says, it's like, the solid growth model. Think of that, where you have a function that goes like this, and it's increasing and concave, and the Onada conditions are satisfied, and therefore it's going to cross the 45-degree line only once. Right? And if you take away concavity, you might lose that. So there's a fixed point theorem that extends that to multiple dimensions. Okay. And this, you just check these conditions. If these conditions hold, then your policy operators are going to satisfy the conditions of that theorem, and you're good. So this works nicely for Epstein-Zinn, for example, or for smooth ambiguity models. Any questions? Yeah.
Like, I mean, guess I didn't want to talk about this, but are there kind of equivalents of these proofs for like continuous state, or like do you think there would probably be some?
Yeah, so
and of course, then it depends on the algorithm how you compute and interpolate, but like
but it's kind of like in principle
Yes.
for general state and action spaces. Yeah, the answer is yes, and we've proved some of this stuff. There's still holes there, but for example, the set of the class of models that we just looked at, like contracting, eventually contracting, concave, and so on. These are all based on fixed point theorems that work in infinite dimensions. So in principle, I think it's not going to be hard to extend this stuff. The other nice thing, which is kind of like hiding in the details here, is that because you really care about stability of the policy operators, it's not as complicated as the Bellman operator, which has got a max operation. For example, if I look at something with a max operation wants to make things convex, and that's going to break this concavity. If I just look at the policy operators, it's going to go through. So yeah, we're like halfway through writing volume 2, and I was saying to someone here that when I say I'm halfway through writing a book, that means I'm actually like 15%, if I'm really lucky. Yeah, so far we haven't had any big problems, so hopefully all this stuff is going to go through pretty smooth.
Yeah, sorry, for games then, to go back to kind of your question at the beginning, for games of a strategic interaction, that it's very easy to have non-stable points and multiple optimal. So for these cases, we cannot apply.
So I think that multiplicity is probably occurring at a higher level. So if you, let's say you've got a dynamic game and you fix the policies of one player and now you look at the other player. So his dynamic program is probably going to be stable. It has a well-defined solution. And then I go back to this guy and solve his problem based on this policy. And I get this dynamic program again is going to be pretty well behaved. But the interaction between them, trying to find that equilibrium, is where you get the multiplicity. I think it's at that level where you're going to have the difficulties. This is not really dealing with those equilibrium structures. This is more at the level of the individual. Sound good?
Yeah, sounds good.
Okay, I could go on, but I think you guys have done extremely well to last until now and through this difficult theory lecture. So thanks for sticking with me. It's been great talking to you guys, and I'll be around for questions.
Before everybody goes anywhere, what happens next is we all